Okay, hi everyone. Thank you for attending this BBF knowledge-based webinar about QED, quality of experience delivered, with some real-life examples, implementations, and a technical deep dive. First, a bit of housekeeping. So this webinar is being recorded, so anything you post in the chat can and will be used against you. We suggest if you have any questions, there will be a Q&A at the end of the session. You can write up questions in the Q&A box, and then panelists can choose to answer that in writing or to answer it at the end. Also, I must mention there's a BBF Q1 meeting coming up very soon. If you want to join BBF or attend that, reach out to info@BBF Broadband Forum. I guess that was it for the housekeeping for now. So let's begin. Okay, so hey, I'm Magnus Olden. I will be moderating this webinar, and it's about QED and real-life example implementation and technical deep dive. With me, I have Peter Thompson from PNSol, John Newton from Vodafone, and Bijan Vartagen from Domos. So the agenda. First, I will give a very, very short recap of the first QED webinar. So this is the second of 2 QED webinars in the series. And then Peter will go into how it works, and Jonathan and Bjørn will go into some QED in action, some implementation, and some real-life examples. At the end, there will be a Q&A. So again, post questions if you have them in the Q&A section. Also, any feedback you can give us about what you want to hear more about with regards to QED, please share it with us. Ask in the QED or just in the chat. Again, this webinar is being recorded. Okay, I'll jump right in. So let me do a short recap here. What is QED? Well, QED is a network quality framework that is technology independent, right? Doesn't matter, it can be used for Wi-Fi or for fiber or for cable. It is based on the concept of quality attenuation, or written delta Q, which is turning network quality upside down and looking at how much network quality is being lost per link instead of how much you have. There's also a rich mathematical framework around it, and you can compose links, adding them up. So, adding the Wi-Fi link and the fiber link up makes sense, which it doesn't for things like megabits per second and jitter. There is also ways to dissect and decompose latency, figuring out what is causing it. There's also a lot of tools around quality attenuation and mapping that to requirements and complex requirements. So from simple service level agreements to very complex ones. And then you can also do application class. So you can make a QTA, as it's called in the framework, for video conferencing, for example. And you can make one that is even more complicated and detailed for Zoom. And since Zoom has many different quality levels, you can even make different QTAs for different quality levels of Zoom. So it gives us the mathematical framework to move towards understanding the application outcome. As well, there is a testing procedure that is standardized, it's easy to implement, it fits everywhere. And if you have STAMP or TVAMP, you have everything you need to get started, right? And I must emphasize that this is an open framework. Anyone that wants to can help contribute, and in fact I highly encourage you to contribute and join Broadband Forum and join the PEAT and QED projects. With that, I will hand it over to Peter Thompson, the CTO of PNSol. He's also heading technical marketing and many other things around QED and quality attenuation. Peter? I can see your screen, but I can't hear you.
Hi there. So I'm going to give a bit more of a more detailed technical introduction to quality attenuation. This is in the line of the deep dive. This is I should say this is not the deepest dive we could take. There's quite a lot more mathematical detail behind all this, but I'm not going to go into that very far. So I'm going to talk about the nature of performance. Magnus has already said something about this, but the key thing is that in an ideal world, our systems would always respond instantaneously and never fail. But in practice, this doesn't happen. There is always some delay, and there's always some chance of failure, and so we say there's some attenuation of the quality, and we call this delta Q. So technically, this means performance is something called a privation. So good performance means the absence of attenuation. It's something a bit like darkness or silence. It's the absence of something else. So it's a little bit tricky to get your head around, but it becomes an important point. Of course, quantity also matters. So typically, what we want for a good service is a certain rate or volume of responses with some given bound on their attenuation. So the measure of performance is delta Q. It's the extent of how far away we are from instantaneous and infallible. And so we're combining delay and loss or failure into a single measure. We're treating them together. And this intuitively, this makes sense because in almost all cases, there comes a point where too much delay is as good as failure. If you have to wait too long for something, it might as well never happen. So blending the two things into a single measure actually makes life a lot easier in some ways. So the second thing about it is this always exists because the real world is not perfect. There always are some deviation from instantaneous and infallible. It's something we can look to minimize, but we can't ever eliminate. It's conserved in the sense that if something gets delayed, you can't undelay it. There's no going back in time. And likewise, if something fails, you can't unfail it. You can do things like retry something, but that's in some ways that's a new thing. The original thing still failed, or the original packet was still lost. There are ways to trade aspects of delta Q. So, for example, if we do something like a retry protocol, like in TCP, we're doing that in order to reduce loss. But the trade-off is that if we have to wait for something to be sent again, that will increase delay. Alternatively, we can use queuing and scheduling mechanisms to distribute loss and delay that occurs due to contention for a resource in an unequal way. For example, we could give priority to voice packets in a network, which would cause them to have a lower delay. But it necessarily causes some other packets to have a longer delay because they didn't get to go first. The voice packet went first. So it's something we can in various ways we can trade it. And we can decompose it and combine it. I'll talk more about this in a second, both spatially and also in components, which give us some useful insights. Okay, so the next thing to say about performance is in the network distributed world, things we're interested in start somewhere, but they finish somewhere else. So just as a simple example, sending a packet from A to B. So delta Q is something that's measured along a path. It's different from typical measures that you would get out of a piece of equipment, for example, where you're measuring something at just one point. Maybe you're counting the number of packets that go by or something like that. But the delta Qs for these subpaths add up. So delta Q has this useful property that we can add it up along a path. And that's very useful in practical cases that we'll look at in a little while. The other thing is when in our distributed networks, we're sharing resources between different users, applications, and various packet flows. And sharing resources makes the outcome performance variable. But applications and protocols are, of course, designed to deal with this. But they do make some implicit assumptions about this variability. And so it's important to measure that. And so that means we need to have a statistical measure. So performance is distributed and statistical. So ultimately, this means that delta Q is a distribution because all averages lose information. So actually, really what we want is to keep the whole distribution of delay and loss. Even moments and things like centiles aren't the whole story. Here's an example of a couple of cumulative functions that start from the same point and they finish at the same point. So you could both say they deliver 99% within 16 milliseconds, but I think it's pretty obvious that these are very different kinds of performance. And we could come up with other examples that have the same average and the same centile, but still are significantly different. Whereas if we have the full distribution, we can extract everything we want. And one of the important things about distributions is what we call the tail, the kind of the low probability events. And because networks mostly work these days, these rare events can actually have quite a significant impact. So it's important that we represent them and measure them. So as I said, we combine the distribution of delay and the extent of loss together with a mathematical concept called an improper random variable, which is just a random variable which is a total probability of less than 1. And we conveniently represent these using what we call a cumulative density function. So here's an example. You can see this. The way to read this is that there's no chance of anything taking less than 4 units of response time, whatever that is, could be milliseconds. By the time we get to 7 units, we're up to about 50% of things take no longer than that. Where by the time we get up to 12 units, more than 90% are taking less time than that. And so that's what this curve is telling us. So this part of the curve, this is an improper random variable. This part we call the tangible mass, and it encodes the distribution of the response time. But it doesn't quite make it to the top. There's this gap below 1, which we call the intangible mass, and that's where we have the probability of the thing not working at all. And we can compare these things. So here's an example of two different curves. And in this picture, of course, if we go down and to the right, we get more attenuation. Right? Things on are then going to be taking longer, and there's more chance that they don't succeed at all. Remember, less attenuation is better. So because the blue curve is to the left and above of the black curve all the time, it has a lower quality attenuation. So, and mathematically, this is something called a partial order, because these curves might cross and then we couldn't say the one was bigger or smaller than the other. But if they're like this, if they satisfy a relationship like that, which is just a mathematical way of saying what I just said, then we say one of them is definitely smaller. And we can use this to produce a rigorous definition of what we mean by equality attenuation being low enough. So we've talked about this concept of a quantitative timeliness agreement, and that includes a specification of what's the bound we want on quality attenuation. And because of this relationship here, we can definitively say whether or not a delivered quality attenuation is less than what we were supposed to be less than. And this all relates to the way applications interact with networks. Distributed applications they rely on the network to translate information from one place to another. And really, the application doesn't care how the network does this. It only cares how long it takes and if it might fail. So really, the quality attenuation is the thing that the application is concerned with. So when we talk about insufficient bandwidth, we can reframe that as meaning at the load we're offering, the loss and or delay that we're receiving exceeds the bound that we're prepared to take. And if we have, we can even represent a connectivity failure by saying the quality attenuation is total. What we're saying here is that the whole achievement of layering of network protocols and so forth, the IP everywhere model, has insulated the application from most of the details of the network, and really the delta Q is the way the network impacts the application. So to summarize, quality attenuation is distributed, it combines delay and failure, it's statistical, and it goes beyond bandwidth because it incorporates the notion of bandwidth as a special case. Okay, I'm going to move out of the theoretical now and get into some more practical details about how we would actually measure this. So we said delta Q is a distribution. How do we measure a distribution? So we measure a distribution by sampling it. So to sample the delta Q from A to B, we time how long packets take to go from A to B and how often they get lost. Of course, the delta Q may depend on factors such as the packet size, so we need to get a good spread of those parameters to get the full picture. And because it's a distributed measure, we have to combine observations made at different network elements so that we can follow the transit of a packet along the network path. And if we make sequences of observations at various points, we can then compute the delta Q of the individual path segments. So this is kind of how it works. At the top, we've got the path the packets are taking. A, B, and C are places at which we make observations. So each of them delivers as a whole a kind of series of kind of records, if you like, with here was a packet, this is how big it was, this is when I saw it. And then all of those get combined, correlated, you know, which packet at which point corresponds to the same packet at another point, and then we can work out what the delta Q was. And we can use established mechanisms such as various two-way active measurement protocols like TWAMP and STAMP. And we're going to have a bit more about that later on in this webinar. But we do also need to make sure we can make measurements that don't rely on any of those features, other than the fact that it's providing us with IP connectivity. We can measure delta Q by making observations of packets that we're just going by anyway. But again, we don't necessarily want to have to rely on existing traffic. So for these reasons, we specify a method of how do we generate, observe, test packets that provide a reliable estimate. And this is what the Broadband Forum technical report 452.1 describes, as well as the theoretical background that I've already gone through. So this would be a typical example of how it would work. We have a packet generator, which is going to send some packets out into the network to some remote location where they get observed, and they get turned around, and we send them back again. And then we take the times when those packets went in and out of the various places, take all those traces and analyze them. So each packet gets sent on a loop, we time them in and out, we match these traces to analyze the performance. And then that gives us information about the whole round trip and about each direction. Excuse me. So what's the data we need to collect? We need to know which measurement stream it is. We might have a lot of different things going on. So we need to make sure we can distinguish packets belonging to one measurement stream from another. We need to know the size of what we're looking at, because the delta Q will depend on that. We need to know enough about the packets to know which one it is within the stream we're looking at. So we can just use a sequence number, for example. And we need to know the local time that it was observed at. The key feature here is that we don't need accurate clocks, because we can deal with offsets. Because we measure a round trip, we can deal with offsets as part of the analysis process. So we can work out the duration of each packet transit, or whether it failed. If we see it in A and B, but we don't see it at C, then it looks like it got lost. So we can do this, all the way across a whole chain of segments, potentially just using the same set of test packets that we just observe in different places. And then the delta Q end to end is literally composed of the sum of the delta Qs along the path. So that's how we can measure it. When we've got this information, what can we do with it? Well, one thing we can do with it is to extract a bit more structure and information. So the sort of results we get are something like this. This would be a series of transit times of packets as we over the period that we were doing some measurement. So this is the raw delay. We could turn that into a distribution, which is fine, but this is, maybe we can do better. So one of the things we can do is to say, well, let's factor out the way that this depends on packet size. So we can sort all this data by packet size instead of by the time at which it happened. And we start to see some structure. So we're going to use this to decompose the round trip time into 3 components, both upstream and downstream. And potentially each of these is statistical, but sometimes we can reduce them to a number, which makes life a bit simpler. So we fit a line to this distribution by size. We can extrapolate it to say, okay, let's get away from what the actual minimum packet size is and say, if we could take this all the way to 0, how long would it take? This is the sort of theoretical minimum time. And we call this the G component, the geographic delay. And obviously this is related to things like how far apart things are and the speed of light. We can then say, okay, how much longer does it take to send a packet which is not 0 size? And that's a function of the packet size. In simple cases, we can just say, well, it's a straight line, and we can reduce S to a number, which is the slope of the line. And then what's left over is the variable part of the delay, which is really determined by things like network load and congestion and so forth. Serialization delay really depends on the interface speed. Okay, so we can break it down into these components. Each of them could have some loss. If the loss rate was just a sort of noise floor that always happened, it would be part of G. If it depended on the packet size, for example, we had some probability of corruption of each byte, and if we have a corrupted byte, we lose the whole packet. Obviously, that gets worse the bigger the packet is. And if it varies with load, it's then a part of V. Most loss in typical broadband networks is due to the sharing of resources and buffers getting overloaded. So it mostly goes into V as the tangible mass, the intangible mass of the improper random variable, also known as the 0th moment of the distribution. Okay, so delta Q adds up both horizontally along the path, as we've seen, but it also adds up vertically among components, and it does both at once. So this enables us to get a very granular view of quality attenuation. We can divide it into space and into components at the same time, and this gives us a really fine view of what's happening in networks and helps us to isolate issues and so forth. Okay. That's my part. Thank you very much. I'm now going to hand over to Jonathan Newton.
Yes, Jonathan Newton is the next speaker. So first, if you have any questions, and I do not believe none of you have any questions, if you have any question, please ask them in the Q&A box. I'm sure there are other people who wonders the same thing as you. Okay, so ready for some action? Here's our first action man. Jonathan Newton is a principal network architect in the Vodafone Fixed Access Center of Excellence. He covers technology, strategy, and best practices and innovation with remit across Vodafone's countries of operations. His background is in design, implementation, and performance management of large-scale international communication networks. Jonathan, over to you.
Wonderful. Thank you very much, Magnus. So hello, everyone. So what I'm going to do in the next few minutes is just take you through a couple of things. First of all, how an operator might consider an implementation of the QED framework. And then secondly, to look at some real life example results and just describe a little bit more about some of the aspects that that Peter's gone through in the first section there and what they look like in those real results. So in this first chart, I'm going to start at the bottom of this, slightly counterintuitively. So there's a few things we need to be able to do to implement the QED framework. And the first one is about getting the measurements in place. And that may seem a little bit daunting to begin with if we're thinking we've got to completely change how we measure everything in order to be able to do some end-to-end analysis of our quality attenuation. But that's not necessarily true. So the way we've looked at this is around sort of leveraging our existing and new test capabilities. So from existing capabilities, we might have dedicated applications, apps on phones or probes that we can deploy out on customer sites. Things that we may have built in-house, and we can small upgrades to those can create the capability to provide results that can be analyzed under QED. The next one, though, is interesting because most operators have a large number of sort of network level probes, generally using standardized test methodologies such as TWAMP, so that's RFC 6038, and STAMP, which is RFC 8762. And those can be used. If you've got those sort of capabilities, then you've got that prerequisite to be able to do all of the generation and monitoring of test sample data. And therefore, you've got that prerequisite. It's just a small sort of increment then to be able to use that to feed into a delta Q QED style analysis. And the last way of really getting this data from our network now is in the world of virtualization, where we can start to deploy things on demand where we need to. So at sort of network cloud locations or edge cloud locations. So if you're seeing particular problems, it does allow you then even to introduce additional testing capabilities, sort of hone down on those issues. So they've got those sort of key three test capabilities and ways to actually measure. So the next question moving up is about where, I guess, to measure. And ideally you'd measure everywhere. You don't necessarily need to measure everywhere. So some of the key areas we've looked at are shown here. So at the bottom there, we've got measuring from the broadband, from the broadband router to the end host. So that's sort of the in-home domain, and a bit more about that later, actually, in the next section. Can also look just within our network. So this is the next layer above here is looking from perhaps between transit routers for the internet to the service edge, which would be the broadband network gateway in this case. And this is where probably these sort of large scale network probes that already exist come into play. Or from the broadband router right down to the broadband router on the customer side right up to the service edge of the broadband network gateway. And that aspect of it is quite important. That really starts to cover all the way across from where the service is delivered down to the home and including the access network. And this is something that Broadband Forum has standards about how to monitor those aspects around TR390. And there's work on a new issue 2 of that, which includes things like the STAMP protocol. And lastly, then, really, I guess there's other aspects within the network, which is then from the service edge down to the access node. There is also the ability to run end-to-end, right the way from the customer device up to perhaps the server or offering a particular service, or into a sort of a cloud data center, for example. And those techniques actually not necessarily using some of the techniques that I've talked about below, but we've done some proof of concepts on things like using WebRTC to understand and monitor those. So it was, we looked at that proof of concept ourselves, and it was relatively straightforward actually to implement and see if we can pull out some analysis for delta Q from that kind of level at the application level. And then the key for this, as Peter already said, this is composable, so we can add these up and even take them away. And it allows us, with these segments, we can segment out the network. We can understand the performance sort of on an end-to-end basis and see how each of these segments contribute in an overall to the overall customer quality of experience. So you feed all of that up now using perhaps lots of different locations and lots of different techniques. We can feed that up into one analysis capability, which gives us a single way of looking at the performance delivered to our customers end to end over the network and how each of the segments contribute to that performance. So looking now at some of these example results. So first of all, this chart shows the characterization of different access technologies. What we can see here on the charts is the green section is that geographic delay, the G component that Peter talked about. The blue section is the variable aspect related to the packet size. And the red and the yellow correspond to the variable part, the V component of that delta Q. And we've just got it's split into a mean and a standard deviation just to show how significant the V component may or may not be to the particular customer. So these charts are over time, so the number of tests over time. So you can see, traveling, it's taken in December 2017, so it's quite relatively old time data, but it's important because this is where we started. We started looking at the characterization of different access technologies, and you can see how each of the technologies has a different characterization. So we can see how the GPON one has a relatively small GS and V. We can see how the 4G in this particular line had sort of a relatively large component from each, the GS and the V. And the VDSL had a larger G probably than the GPON, larger S really because it's a lower speed line. And then we can see how the variability impacts, and you can see how the variability is, as Peter said before, was really the key aspect for these two broadband lines as you start going up through the speed. But actually there was a little bit more variability for a fixed mobile access 4G line. And once we've done this, it's quite straightforward then. If we continue to monitor these lines, you can start to see sort of misconfiguration. So you can start to see, well, actually, normally we'd see the G quite low for GPON. You can pick out misconfigurations or performance issues quite quickly that you wouldn't normally expect. And it's really helpful splitting out these aspects into these different GS and V aspects to be able to see this. So another example result, perhaps a little bit more complicated to look at. We're homing down here on the G and the S. So in this case, we're not looking at the variability at all. And what we're comparing is the geographic delay and the serialization delay, or the packet length, the delay that varies based upon packet length, for a fiber to the home and a fixed mobile substitution lines. And there's a few things that are really interesting coming out of this chart. First of all, that just inherent in these results, you can see some interesting network events. So just looking at the G component, which is the green line here for this 4G line, for this 4G fixed mobile substitution line, you can actually see a backhaul reroute events with these different base latencies appearing. Okay, so you can start seeing, it's useful then to be able to pick these out and analyze them, be able to identify them in the results. And the second aspect I think we can see here is that the S is relatively large for the 4G aspect, and that's kind of important to note, because we're in a world where, yes, our speeds are increasing, and normally you'd expect the S component to become less and less important. But it does continue to be important, especially in a converged world where we're looking at things like fixed wireless access, hybrid access, where we're splitting traffic across multiple access lines. Understanding the performance of lines to this level of detail allows us to perhaps make much more sensible and forward-looking decisions around how and where to place particular applications where we're making use of multiple different access lines. And it's also true that the S can be important in sort of long ADSL connections still, perhaps on Wi-Fi, and even in certain network failure or network faults, perhaps misconfigurations, we can see that the S starts to become quite important. But again, here, if we look at at a plot of one against the other here, we can see the fiber to the home performance is relatively low in terms of the given delay, and also relatively low in terms of the serialization delay. And we can see how you can compare and plot different performance of different access line types relatively straightforwardly between each other, and see how the different technology compares. Okay, the last example I give, this one's a lot more detailed. It shows extra information here, things like the cumulative distributions. And the reason for picking this particular chart to look at is that we're now splitting between the upstream and the downstream components. And you can see this particular one was a VDSL line, and we were monitoring from a customer home on VDSL up into AWS in Frankfurt. And we could see that the performance wasn't ideal, but what it was interesting is we could see that on the left-hand side, where we've got upstream, you can see there's a relatively consistent performance. The delay is consistent. If we look at the variability, just the V component, then actually that's relatively consistent. And if we plot the cumulative distributions, it's quite a nice sharp vertical line here. So we can see that the upstream was quite a consistent, good performing solution. But actually, when we come to the downstream, you can see this is where the problem started to come. So the observed delay and the variability is now much more pronounced. And if you plot the cumulative distribution here, we start to see that the lines moved off to the right here. So we've got greater quality attenuation. And it's important there, we can by splitting these two upstream and downstream components and looking at it from the distribution perspective, we can quite easily see how each of those components, both upstream and downstream, contributes to the overall performance. And we can narrow down on the fact that this was an upstream performance issue on this particular line. Okay, that was all I have to show you for those results. So thank you very much, and I think we'll pass over to Magnus again.
Thanks a lot, Jonathan. Well, the questions have started coming in the Q&A section. That is awesome. Please keep them coming. So next up is my colleague, Bjørn Vartagen. He is the head of research at Domos. That's his day job. He's also a PhD candidate applying quality attenuation, or delta Q, to Wi-Fi networks. So I'll hand it over to you.
Thanks, Magnus. Yeah, so at Domos, we use QED tools to analyze and optimize Wi-Fi networks. And I will go through a couple of examples. First, a top-down approach, and then a bottom-up approach using QED. So Wi-Fi latency is large and somewhat unpredictable. And we found these QED tools very useful in capturing this latency variation and making analysis and optimization feasible. So first, with the top-down approach, we have run a QED sampler at scale and collected a data set. And then we can use that data set to find the samples that stand out with higher latency and loss than what is normal or desired on Wi-Fi. And then we can analyze to find plausible causes for those problems, and then investigate further. And then the final point here, I won't go into detail on this, but I wanted to mention that once you have a QED sampler running at scale, it's very easy to do A/B testing, for instance, of new solutions. So here is an excerpt from the data set we collected. And the top row here is the 2.4 gigahertz network, and then the bottom row is the 5 gigahertz network. And then the leftmost column is the best possible signal strength, and then the signal strength decreases as you go right. So there are a few salient points here. I would point out first that the 5 gigahertz network is significantly better than the 2.4 gigahertz network. That was expected. And then there is another thing, which is as the signal strength increases, you don't really see all of the latency problems going away. And this led us to investigate further, and we found the problem, or one of the problems. So this chart shows the rate on the y-axis as a function of signal strength. And the rate is the throughput speed of the Wi-Fi link. And you would expect that as the signal strength increases, you also get a higher rate, because the radio is able to get more data through when the signal is stronger, right? But we found that especially in the upstream direction from station to access point, but also in the other direction, we have quite a lot of cases where the signal strength is very good, but the rate is very low. So this is clearly a problem, because this causes some stations to use a lot of the available airtime on the radio, and that causes queuing, which then translates to latency and packet loss for all the users. So having identified this problem, we're able to design tests to diagnose it, and we can configure the network to minimize the impact and mitigate the problem. And then the bottom-up approach. And what we've done here is to model the system using the mathematics of QED. So we have a model of the Wi-Fi protocol in the QED framework. And then we can use that to analyze the behavior of the Wi-Fi protocol under different conditions. And I have selected the RTS CTS, or request to send, clear to send protocol as an example here. So on the left side here, you see the normal operations of the Wi-Fi protocol. So when a sender wins the opportunity to transmit data on the wireless medium, it transmits some data and then waits for an ACK. But if either the data or the ACK is lost, then all of this time spent transmitting the data and waiting for the ACK is wasted. So in the case of a collision, we lose this time. And the RTS-CTS mechanism, if you enable that, then the sender will first send a request to send packet, and then only if it receives a clear to send packet will it then transmit data and wait for the ACK. And what this does is that if either the RTS or the CTS packet is lost, then we only waste the time to do that handshake instead of the entire data transmission. So we have plotted this for different scenarios, and this heat map shows the impact on throughput from enabling RTS-CTS. So the blue is throughput increases, and red is throughput decreases. So we see here that when there are many stations and very large packets, we have a strong blue color, and we have almost 15% increase in throughput from enabling RTS-CTS, which is, I mean, a high number of stations and large packet sizes is ideal for RTS-CTS, because you will have a lot of collisions, and each collision will take a lot of time. So reducing the impact of each collision improves throughput in this case. But then in the other case down here, we have only 2 stations and very small packets. And then you can see that the total throughput of the Wi-Fi link decreases by about 8–9%. And over on the right side, you can see the latency CDFs of the 2 cases. So blue is the baseline Wi-Fi without RTS-CTS, and then the yellow is with RTS-CTS enabled. And the average latency is higher in the RTS-CTS case because of the added overhead, but the worst case latency is actually smaller in this case. So what the QED tools enables us to do here is to model this and to make informed decisions about when to enable different protocol features. Because, for instance, here, if you're running an interactive application, you might want to enable RTS-CTS because it reduces the worst case latency at the cost of some throughput, but that might be a trade-off that you're willing to make in some cases. All right, so this is the long form summary for the distribution of the slides, and this is the short form summary. So QED lets you find and analyze the sources of latency and packet loss in your network. And with that, thank you for your attention, and we can go to questions.
Thanks a lot, Bjørn. Okay, so we have quite a few questions coming in. There's a lot of them that are about the same. So how do you actually implement this in the network? Do you use iPer for Chariot? There was link pointing to stamp. What is the relevance? I think I will let Peter answer these questions. Peter?
Yeah. So the Broadband Forum Open Standard basically defines the architecture you need to do measurements that are of delta Q, and we're working on a follow-up technical report, which would be called TR 452.2. Which goes into then more detail about how you would implement that using the existing protocols like STAMP and TWAMP and so forth that Jonathan mentioned in his talk. So that's a work in progress. And then it becomes equally it's open to various vendors, perhaps people making test and measurement equipment or virtual facilities and networks and so forth to potentially add the corresponding features into their offerings. So this is something that we're developing as on behalf of the whole industry, and there are a variety of ways, as Jonathan Newton was talking about earlier. What we're also trying to work towards is commonality between these different methods, so that it becomes straightforward to combine measurements taken in different ways to get the kind of complete end-to-end view. So existing tools can be used. You have to use them in a slightly different way from what they're typically there for. I mean, iPerf is typically used as a mechanism for measuring kind of limiting capacity, whereas what we're looking for here is the ability to measure transit times between different points. But the existing protocols like STAMP and so forth do have that facility, and with some slight extensions, for example, to enable us to vary the packet size more, they're perfectly suitable for doing that. So that's really the picture in terms of doing this. It's a bit different from what people have typically done before in terms of network monitoring. So you have to vary things a bit. It's not necessarily something you can get off the shelf right now, but the gap between what we have and where we need to be is quite small, and it's being filled in pretty quickly.
So short summary is that there are multiple ways of measuring quality attenuation, which brings me to the next question. I think I will throw that to you as well. Delta Q QED, quality attenuation. What is the deal? Why are we talking about these things? Could you give me the 2 second or 30 second?
Yeah, okay. So naming of things is always tricky. Quality attenuation and delta Q are the same thing. One's just a bit more of a mathematical notation that we can more easily put in formulas and so forth. QED is a program of the Broadband Forum. It's a work stream. So that's the thing which is generating these technical reports and marketing reports and so forth, which are based on these notions of quality attenuation, but it goes beyond that. It defines use cases and ultimately conformance tests and so forth. All of that is part of QED. I hope that answers the question.
I think it did. Okay, 4G FMS delta QG is high. Is that purely due to propagation, or does it include some aspect of the radio? Is radio propagation is faster than fiber? Should I repeat that, or was it clear? Peter?
Sure. Okay, so that's a good question, and that would be a question that could. The way to answer that question would be to have a more granular delta Q measurement. So if you look at this and you say the G on this is quite high, why is that? Where is that being accumulated? With more measurement points on the end-to-end path, we could answer that. Unfortunately, this is kind of old, as Jonathan was saying, this is some quite old data, and we were really only measuring it end-to-end. So we don't have that intermediate measurement point. But what I would guess is that because the G component is not just due to propagation over distance, that's one part of it, but it also includes any kind of fixed overheads which you incur regardless of what the packet size is or what the load on the system is. So when you have complex radio link protocols, for example, the time it takes to execute those then becomes kind of part of G. So I would suspect that actually the reason that G is higher is here in the 4G case as compared to VDSL or fiber is basically that the protocols involved are more complicated and there are more steps that you have to go through to transfer any piece of data, and that's where it shows up. That would be my guess. But actually, the real way to answer that question would be to do a more granular QED analysis.
Perfect. Okay, questionnaire. I'll send that to Jonathan. Would the demarcation point again be changed for ISPs? Jonathan, if you are answering, you are.
I'm here, Magnus. I was just thinking when we're thinking about the demarcation point. So I don't think the demarcation point changes if we're meaning where the handoff is necessarily to the subscriber. So ISPs for quite a while now have been increasingly responsible for the Wi-Fi in the customer's home. And that means really, so the demarcation is historically that would definitely demarcation between the ISP and the customer would have been sort of at the entrance to the home, but that's long since changed, where we're now really taking more and more responsibility for things like the Wi-Fi and the connectivity in the home, and that's why in a lot of cases this is why increasing capability to monitor and understand the performance of all of those aspects right down to the end device is really important. A lot of our if you like calls and issues that our end customers have and now really relate to things like the Wi-Fi as well. So is it changing again? I'm not sure it's changing again. I think it's already changed to being an end-to-end need for ISPs to understand the performance that's being delivered to customers.
I guess that's one of the beauties of the quality attenuation or delta Q is that you can actually add these together, right? You can measure the quality attenuation over Wi-Fi and add that together with what you're having on your access and with the core, right? So even if you had to move the demarcation point one more time, you could actually just add that measurement on top of it again, right?
Yeah, exactly. Having the one framework to understand this performance on an end-to-end basis, you know, you can look at this from, you know, if a particular ISP is using a wholesale supplier, then you can look at the quality that supplier introduces into the chain. You can look at the quality of the attenuation that the Wi-Fi introduces into the chain, that your own network introduces, and even up towards the sort of the application provider and into the cloud. So it's a great technical way of understanding that end-to-end supply chain and seeing how each component contributes.
Exactly. I'll just continue. I think now, you know, all of the panelists just jump in if you want to answer. Speed tests are common. So how can QED measurement replace speed test? If I run a QED test from RG to network server, like a speed test server location, how can it be reported to advise the customer that everything is okay?
Okay, let me say something on this. I wouldn't say QED measurements replace a speed test, but it's complementary to the speed test. What the thing is, okay, let me just back up a little bit. Historically, the main limiting factor on the kind of delivered customer experience has been the speed of the line. Okay, when you had a 2 megabit line, if you could upgrade to a 4 megabit line, it was really twice as good. But now we're up to kind of, you know, we're getting into the gigabit era. You know, if you go from a gigabit to 2 gigabits, is it twice as good? Probably not. In fact, most end users probably won't even notice the difference. So the speed test, while the speed test is still, you know, a kind of important measure to check that the speed that you're supposed to be getting is the speed that you are getting, it's becoming less and less important as the thing that tells you how good an experience you can expect for anything other than a speed test. And this is where the QED measurements come in. They are really more to do with, well, this is what applications which are not saturating the line are going to experience. And that's then much more relatable to, you know, what's the performance impact on an application like you know, Zoom call, for example, which typically isn't going to saturate your line. So the capacity of the line doesn't really matter. You know, if I'm doing a 10 megabit stream, it doesn't really matter whether my line is 50 megabits or 100 megabits or a gigabit. It doesn't make any difference. Or very little. But if you know, if the delay that I'm getting is you know, 50 milliseconds or 500 milliseconds, that makes a big difference to the quality of experience that I'm getting. So it's something that's really adding more dimensions to the performance landscape. And you know, unfortunately, this makes it more complicated to talk about. It's, you know, it's like you can't just have a single number that represents the kind of capability of broadband, but unfortunately that's what life's like.
But what you actually can do is you can create a QTA for example, Zoom. Then you can give some likelihood of that link to work, right? You can go from an end user's home, right? You can say, okay, here is in peak hours, there is a 90x% likelihood that Zoom will work, right? For example. So there are ways to translate this into more end user understandable things, right? Even more so than megabits per second, I would say. Okay, our time's up. There are more questions in the Q&A. Thanks for them. I think for some of these, we will actually reach out to you through Broadband Forum with answers. So thanks for everyone for coming. Thanks to Broadband Forum for having us panelists, and thanks to all the panelists. Okay, goodbye.